Hello, thank you for coming to the talk today. Today, basically the aim of the talk is to prove Fermat's sum of two squares theorem, which basically it says that if a prime is congruent to 1 mod 4, then you can write it as a sum of two squares. And the way we're going to prove this theorem is using the ideas from lattices, and specifically we're going to use Minkowski's theorem to prove it. So a lattice in two dimensions can be generated by two vectors. Let's call them V and W. And the lattice generated by these two vectors, V and W, is the set of all vectors that can be written as an integer multiple of V. Sorry, my pen stopped working. An integer multiple of V plus an integer multiple of W. And the way this would look over here is something like something like this. And we say that each intersection of the lines over here is a lattice point. And so one question we can ask about this is, suppose we drew a region on the lattice. Sorry, my pen has stopped working again. Suppose we drew a region on this lattice. One question we can ask is, when does this region contain a lattice point? And it seems like if you increase the area of your region, then you're more likely to contain a lattice point, and if the area is smaller, then you're less likely to contain one. So is this true in general? The answer is it turns out to not be true, because you can come up with some kind of counterexamples. For example, if this was the lattice, then if you drew a region that kind of snakes around the lattice points like this, you could keep extending the region on forever and increasing the area of this without bound, but still not contain any lattice points. So it turns out that this is actually not true, but the reason it turned out to not be true is because the region we have over here kind of has holes in it. So what that means is if you take 2 points in the region and you connect a line between them, you can pass over an area which is not contained in the region. And so to fix this problem, we'll introduce a concept called convexity. And we say that a region is convex if whenever you take 2 points in the region and you draw a line connecting them, then every single point on that line is also contained within the region. So if we require our region to be convex, is it true that we do have some kind of thing we can say about the size of a region corresponding to whether it contains a lattice point or not? It turns out again this is not true because, for example, if you just imagine that this is your lattice and you draw a rectangle like this. If you extended this rectangle in both directions vertically, then you could also increase the area of this as far as you want and never contain a lattice point. So again, it's not true, but this time the way we can fix this problem is simply by translating the rectangle until one lattice point is in it. And then you can see that infinitely many lattice points come inside your rectangle. And so the way that we kind of captured this idea of having one central lattice point in our region is the concept of being centrally symmetric. I think I'm going to switch to slides because my pen is still not working, and I think it will just be easier to present using slides. So I'm going to change over now. Okay. Okay. Are you able to see my screen now?
Yep, all good.
Okay, great. This should probably be easier. So, yeah, we call a region centrally symmetric if it contains the origin, and for every vector it contains, call it x, it also contains minus x. And so now, if we require our region to be both centrally symmetric and convex, it turns out that it is actually true that we can say something about the size of the region and how that relates to whether it contains a lattice point or not. And this is the whole idea of this is captured in Minkowski's theorem. And Minkowski's theorem, basically what it says is if you have a lattice generated by vectors u and w, and you have a region on this lattice which is both convex and centrally symmetric, then if the area of this region is greater than 4 times the area of the parallelogram that you form from the vectors u and w, then the region must contain a lattice point that is not the origin. And now that we have Minkowski's theorem, we can actually use it to prove our theorem about primes and square numbers. So what the theorem says is, if a prime number is congruent to 1 mod 4, then you can write it as a sum of two square numbers. And it's also true that if the prime is not congruent to 1 mod 4, and also this is an odd prime, so if it's 2, you can write it as 1 squared plus 1 squared. But for every other prime, it's either 1 mod 4 or 3 mod 4. And it turns out that whenever it's 3 mod 4, you can't write it as a sum of two square numbers, and when it's 1 mod 4, you can. The case showing that when it's 3 mod 4, you can't write it as a sum of two square numbers turns out to be this sort of easier direction to prove because you can kind of go case by case and show that whatever case you're in, things don't work. But to show that when your prime is 1 mod 4, you can write it as a sum of two squares. This is kind of like the interesting part of the theorem because like it is not at all obvious why it's true. But now we're going to try and use Minkowski's theorem to prove it. So before we start on the proof, we will need this following fact from number theory. And it says that if your prime is congruent to 1 mod 4, then there exists some integer, z, such that z squared plus 1 is a multiple of p. And specifically, if you take p minus 1 over 2 factorial, that is a solution to this congruence. So from now on, we'll take z to be this particular number. And what we're going to do is first we'll make a lattice. The way the lattice will look is it has one horizontal vector, which has x component p, y component 0. And then we'll have another vector which has x component z and y component 1. Then the area of this parallelogram will be p, because the base of the parallelogram is p and the height of it is 1. And if you take any point on this lattice, you can write it as a times p0 plus b times z1, where a and b are integers. And so now if we take any vector on this lattice and we look at the length of it squared, on the left-hand side we get x squared plus y squared. And on the right-hand side, by expanding, we get ap plus bz whole squared plus b squared. And the a squared p squared goes away when you look at it mod p. And the 2ap bz term also goes away because both of them are divisible by p. And what you're left with is b squared times z squared plus 1. But the way that we chose z squared plus 1 is so that it's congruent to 0 mod p over here. And so the whole expression is equal to 0 mod p. And what this means is that x squared plus y squared is actually a multiple of p for any x and y that are on our lattice. And So we can write x squared plus y squared as kp for some integer k that is bigger than 0, bigger than or equal to 0. And if we assume that x and y is not the origin, then we also know k is not equal to 0. So we have that k is either 1, 2, 3, so on. And if we could show that for some lattice point we get k equals 1, then we'd be able to show that you can write p as a sum of two squares. And so this is where we're going to use Minkowski's theorem. So the area of the parallelogram of this lattice that we've chosen is P. And so if you remember, Minkowski's theorem said that if the area of your region is greater than 4P, then you can say that it contains a lattice point that's not the origin. So our aim is to create some region that has an area that's bigger than 4P, and then we'll use Minkowski's theorem to show it has a point in it, a lattice point. And then we will know that x squared plus y squared is equal to kp for that vector xy. And then it would be enough to show that the length of that vector squared must be less than 2p. Because if it's less than 2p and it's not the origin, then it must be equal to p. So that's kind of the overview of what we're going to try and do. Since we want to find a lattice point whose distance squared from the origin is less than 2p, we can consider a circle that has radius root 2p. And the area of that will be 2 pi p, which is bigger than 4p. And so now we can apply Minkowski's theorem, which tells us that the circle must contain some non-zero lattice point. Let's call that xy. And now, since xy lies inside this circle with radius root 2p, we know that for any point inside the circle, the distance of it from the origin squared is less than 2p. And since it's not the origin, it's bigger than 0. And we also know that x squared plus y squared is equal to a multiple of p. And so the only possibility we're left with is that x squared plus y squared is equal to p. And so we have found the x and y such that x squared plus y squared is equal to our prime. And that's the end of the proof. So I said before that in the other direction, if p is congruent to 3 mod 4 instead of 1 mod 4, it's actually not possible to do this. And the reason that that is true is if you look at everything mod 4, the only possibilities so suppose you had a number. It can be either 0, 1, 2, or 3 mod 4. And if it's 0 mod 4, then it squares to give 0 mod 4 again. If it's 1 mod 4, it also squares to give 1 mod 4 again. If it's 2 mod 4, then when you square it, you get 4, which is 0 mod 4. And if it's 3 mod 4, then it squares to give 1 mod 4. So then if you suppose that you could write x squared plus y squared being equal to p, you know x squared can only be either 0 or 1, because every number when it's squared is either 0 or 1 mod 4. Same goes for y squared. So the only possibilities we're left with is 0 plus 0, 0 plus 1, 1 plus 0, or 1 plus 1. And in each of these cases, we get either 0, 1, or 2 mod 4 as our value. But the thing is, we wanted it to be equal to a prime that is 3 mod 4. And so that's why when your prime is 3 mod 4, you can't write it as a sum of two squares. And when it's 1 mod 4, because of this proof, you can write it as a sum of two squares, which I think is a really neat result. So that's the end of the talk. Hope you enjoyed.
Thank you very much. I can never find the clapping on here anymore. It seems to have disappeared. There it is. I found it.
Someone has found it. Yes.
We found
Thank
it.
you.
Very good.
Does
So,
anyone have any questions?
any questions here? I've got one, but I would like to open up to the rest of the field. So
Okay.
you can either unmute yourself or pop it in the chat, and I'll read it out for you basically as much as you want.
Okay. I see
Go
a
ahead.
question.
Is that me?
Yes.
All right. Hi, Anya. Congratulations.
Thank you.
So I'm afraid I'm not a mathematician, I did math and my undergraduate degree many years ago, but not number theory. So maybe can you explain what are some applications of this project? I know that there is something called lattice cryptography or something like this. Is that at all related? Anyway, yes. What are
Mhm.
some applications?
Okay, so in terms of applications of Minkowski's theorem, I can think of like other places where you can use, actually Minkowski's theorem is like something that you can use in all kinds of areas of maths. And this is like a very kind of niche application that I'd never seen before. So it's like, it's a statement from like geometry, right? But you can apply it to lots of questions in number theory. So someone just told me today that you can use it to also prove that there are solutions to Pell's equation, which I think is like x squared minus dy squared of that form. So it turns out that this thing about lattices can be used to answer lots of questions about whether equations have solutions or not. So if you want to determine whether some kind of equation has a solution or not, you can apply this technique of lattices. Um, in terms of applications of the actual Fermat's sum of two squares theorem, I don't really think it has applications in like the like usual sense of the word. It's just kind of, it's just like the question is when can you write a prime number as a sum of two square numbers? And it answers that. Um, I guess there's lots of questions like that you can ask, and this is kind of the starting point of all of those. So this is like the basic one, splitting a number into two square numbers. But then you can kind of increase that up to what about three square numbers? What about four? And then it turns out that you can write every number as a sum of four square numbers. So this is almost like a starting point for explorations of that kind. Um, but yeah, I guess the only application it has is kind of in like exploring number theory kind of questions. Yeah,
Okay, makes sense. Thank you.
thank you.
I also really like the kind of chalk. We call it chalkboard, but it's not chalkboard, right?
Mhm.
The kind of writing style.
I wish it worked, but my pen seems to like not be working well today, so then I just thought I'll switch back over.
That's fine. You had a backup plan, so that's great. Thank you.
Thank you.
I know that they use lattices in operational research when you're picking like locations that have to be in specific parts of a lattice. They use it there as well for like real life applications. So yeah, if
Yeah.
you're interested in lattices, that's a good place to look at as well. I don't know the exact part of the field, but I remember going to a talk on it and being like, oh, I didn't realize you could use it there. So yeah, there's definitely some stuff.
I
Um,
mean, I try and solve structures of proteins, and there you work with a lot of lattices
mm.
because proteins crystallize and they crystallize in different lattices, and then you have to figure out how from the map of electron density how that translate into protein structure. So I don't know if maybe this kind of math actually
Oh,
is embedded into a lot of this. I just don't know about it.
that's very cool. I also don't know, but it seems like if there were links, then it would be really interesting. Yeah.
So I've got a couple of questions. One of them is related to your talk, and the other one is just in general. But I'll go and let anyone else, if they have any questions, feel free to put your hand up or pop them in the chat. Um, I get the impression that the way that you've proved this is not the only way, or maybe even the standard way. What would be the standard approach to prove Fermat's sum of two squares?
So the way that I've seen the most commonly is like this windmill proof. It's kind of like you you imagine square numbers as squares, and then I don't know exactly how it goes, but somehow you like try and show that you get a sum of two square numbers, and then you draw like a windmill, and somehow like using the sizes of the um what are they called? Like the arms of the windmill, you can somehow show that it adds up to the prime number. So I've seen that in like a lot of different places, and I think it's like a very famous proof of it. And then there's like another very, very standard proof, but that one uses kind of more theory. So that uses like the idea of Gaussian integers, which is basically numbers that are of the form a plus bi, and a and b are both integers. And it uses quite a few results from there. So it kind of uses the idea of like unique factorization in this like a plus bi kind of thing. And that is also quite a common proof. But yeah, this one is like also when I first saw it, I was completely surprised. Like it is not really a standard proof. Yeah,
It's very elegant though, isn't it? You
it
know,
is
you're
very
not, and the techniques used there don't require some really deep understanding. I think there's a lot of intuition, particularly when you did it and you showed the circle. I was like, I know exactly where this is going now. So it was,
yeah.
I think it's a very nice way to prove it. Um, my other question is, what are your next thoughts? When you're studying, have you got anything in mind for what you want to do in the future?
Honestly, I don't know what I want to do in the future, but I do really like maths. So hopefully something related to maths.
I hope when we see you in 2 years' time presenting for another award, you still have the same enthusiasm. Hopefully, the maths doesn't dry you out. But
Hope so too, honestly.
yeah, you have to loop us back in and give us an update in a couple of years' time. Um, so if no one else has any further questions, I'll happy to let Anya take a seat and relax for the rest of the seminar. So thank you very much, Anya, for your lovely talk.
Thank you for listening. I'm looking forward to the next one.